So I have my IntelliJ open. So let's start solving this problem here. I will take the same method name as given here in lead code. I'll just mark it as private static. And okay. Now, as mentioned that we are going to solve this problem using top-down approach, where we are using memorization and recursion technique. And the recursion that formula that we found here is that we start with index, comma total. I mean, we maintain the index and total values throughout, and we chose one of the decision trees. And at the end, when we exhaust all the indices, we see that whether we have reached the target total or not. So let's, as mentioned that I will be using a cache here for my memorization. So let's create a cache. So I'm creating a map here with my key as a string. I'll show that why I'm using a string here instead of integer. And I will call it as memo. And I will use new hash map. That's it. And I will use a helper function here because we are actually using a recursive approach and we are adding memorization on top of it, which is the top-down dynamic programming paradigm. So we'll use the same thing. So here I will use a helper function and I will just call it as the same name. But the parameters would be, we will just add our nums and target, same as here, nums and target here. And as we have seen that we are starting with 0, 0 as our base condition here, base index and total, because we are maintaining an index and total at the same time. So I will start with 0, 0. And I will also pass this map here, okay, our memorization map here. And so let me create this create method. So in IntelliJ, it's quite easy to create. So this part is index, right? So I'm passing index here, and here I'm passing total. Remaining tags are good. Okay. I'm just marking this as final and making it easier to look at. So each parameters I have done like this. And okay, let's start solving this problem here. So here, for all the recursive solutions that we have, we always have a base condition. So for the base condition, we see that once we reach the final, once we exhaust all the index elements, so for example, at this case, we have exhausted all the elements, then we check whether the total is equal to target or not. If it's equal to target, then we return the total count as 1, because this corresponds to one case, right? There is one way where we can find the target. So this is one way and we return 1. And if, for example, in this case, if I move from here, and this way, not here, in that case, we have exhausted all the index elements, but the total is still 1. It's not equal to 3. So in that case, we'll return as 0. So this is how we'll keep on calculating this number of ways, and the final solution would be the sum of all this. So let's try to implement the same here. So if this is our base condition, if index that we have passed equals to the nums of length, right? We are actually checking when we are actually reaching the final. We have exhausted all the elements in the array, and then we have to return if the total that we have been tracking equals target, right? In that case, we have to return 1. Otherwise, we have to return 0. So I'm just using this this expression to check for the last if after we have exhausted all the elements from the nums array. Now let me create the string key for this memo map that we have created, and I have chosen index plus. I'm just using this plus to make it unique, because for example, if index is an integer and our total is also an integer, so we need to have a separator in between to correctly identify these two. Sorry, it should be total, not okay. So this is my key. So and I'm using this tilde sign as my separator to easily identify what's index and what's total. Because if we append these two numbers, it would be a new number. Now we check that if our cache, because we don't want to repeat for the same case. So let me write it down first, and then I will explain. Okay, so in the memorization technique, we always check that whether our solution is already provided, we already contain the value or the total for this particular key. I mean, for this index and total, if we already have the value there. This is same scenario as here. When we move to this path from here to here and here, we got at this point our index and total is 1 and 0. Similarly, if we go to this path and this path, again our index is still 1 and 0. So these are like already overlapping with each other. So once we have already calculated by choosing whatever path we have chosen, and we can simply cache this value, what is the value for 1 and 0 finally, and we just use that cached value that we have stored in our map. So in that case, we don't have to repeat these calculations 2 times for various, and there are various decision trees possible for each of the nodes created. Just to avoid to recalculate everything, we just try to see whether we get the same value in the map for that index and total. So if we don't find it, it means that it has not been calculated yet for any of the decision trees. So we'll calculate it here and then store it into this map so that it's not calculated again for the other case. And for that, we see that we again have to call this recursive, because this is a recursive top-down approach. So we'll call this, and we pass this nums target index plus 1, right? Because we have to choose the next element. And here, the first case is that we chose plus, and the second word would be minus, because as you remember, either we, for example, total here is -1. So one condition is that we do +1 for the next element, or in the second case is that we do a -1. So there are 2 possible trees possible from this node. This is the same thing I'm doing here. So if one is like total plus, and the nums of index, right? And we pass the memo again. Sorry, memo, and the same thing. I will just write it in the next line. Everything would be same, but here total minus. Okay, so here one condition is that we get the plus and the minus, and this is the final value that we get it from these 2 recursive conditions. And then finally we put here in the key and the value calculated, right? Because for these 2 overlapping conditions, there are multiple ways where we can we get that, like 2 ways we can go down from here. For example, you can add +1 and do -1. So there are 2 ways possible, and we keep on calculating for all of them. And that's why we have to call findTargetSumWays 2 times, and with total plus and total minus. And then once we calculate this memo, we put this, we calculate this value, we store it into our cached memo. So that's it, guys. This is all about the problem statement. And finally, we have to move in this loop when our cached memo doesn't contain this key, the index and total value, and then we put it. And if it already contains, then it will simply return for this key, right? That's it. So this was the first time we have solved any of the problem using the top-down memorization problem, because I found, again, I said that For this problem, I found that it's much easier to understand using this top-down memorization approach rather than the bottom-up. So let's try to run this problem, whether it works well. So I will use the same example. So it would deliver 5, 1, and the target. Okay, we have got this, and the target given was 3, right? Yes. So let's run this. So I got a correct answer as 5. Let's try to copy this code and run it in lead code. I'll create some space here, and okay, and then I have to write this helper function as well. So just copy this as well, mark it as public, and yes, let's submit this problem. Yeah, so our solution works well. So let's quickly calculate the time and space complexity here. So the time complexity here would be, because we are just using, we are calculating every time only like once for each of the conditions here. So it would be O of n, right? Similarly, for the space complexity, again, for each of the index and total, we are just creating a cached map. So again, it would be O of n. So guys, this was all about this problem statement for this problem for target sum. In the next video, we'll solve the 23rd problem of our tutorial series on dynamic programming, which is jump game, and we'll solve this problem again in lead code. So see you all in the next video.